this video, we're going to talk about section 11.2 in our book, Polynomial Functions. In general, a polynomial p of x can be written in the form a sub n, x to the n, plus a sub n minus 1, x to the n minus 1, plus dot dot dot, plus a sub 1x, plus a sub 0. I know that's a lot of notation to start with, and it can be a little daunting, but don't get overwhelmed by it. What we mean by these a sub different numbers, these are just the numbers that are the coefficients. So, for example, if we had a polynomial p of x is equal to something maybe familiar, x to the second minus 4x plus 5, then we would just say that our a sub 2 is going to be that coefficient of the x squared term. It would just be 1 because that's the number in front of x squared. We would say our a sub 1 is going to be the coefficient of x. That would be a negative 4. And our a sub 0 is going to be what we call the constant, or if you like, the coefficient of x to the 0, and that would be just 5. Now, with a polynomial, we will talk about its degree, and the degree of the polynomial is going to be the exponent in the highest power of x that appears. So in our original general one here, that is a polynomial of degree n. The leading coefficient is going to be that number in front of the highest power of x, regardless of where it may appear in the actual expression. If I can just spell coefficient. So leading coefficient is going to be, in general, we would call it a sub n. In our example, it is going to be just the 1. And we'll talk about the constant. And as I said before, the constant is going to be that number that doesn't have an x next to it, or is the coefficient of x to the 0, if you like, and ours in our example was 5. So I'm going to give some examples here, and I'm going to go through them fairly quickly, but since you're watching this on video, if you want to, after I pose the problem, if you want to pause it and give yourself a chance to answer the question, then you can check it when I read off the answer shortly thereafter. So I'm going to go through, it's 1, 2, 3, I'm going to do 5 different examples here, and I'm going to ask in each case, is the expression that I write, is the following a polynomial? So that's one question, is can we tell if it's a polynomial or not? And a polynomial can only, as we can see up here, it can only involve powers of x that are positive integers. So you could have an x to the 0, you could have x to the 1st, you could have x to the 10th, you could not have x to the 1/2, you could not have an x to the negative 2. That would not be a polynomial. Okay, so first question is each of the following a polynomial? And the second question I'm going to ask is, what is its leading coefficient? Can you identify it, regardless of the order that it may be written in? And I'm also going to ask you, what is the constant? Can you identify what is the constant? Okay, so here's our first one. The first example is going to be y equals 3x to the 5th plus 4x to the 3rd and a plus x to the negative 1. Okay, so now I'm going to give the answers to the first question. Is it a polynomial? No, it is not, because of that x to the negative 1, because that's not a positive exponent. Now, if we answer the question anyway about the leading coefficient, it doesn't really make sense in this context, but just for the practice, the number in front of the highest power of x would be 3, and the constant here, since there is no term that doesn't have an x with it, we would think of the constant as being 0. So let me give a second example. This time we're going to say y is equal to x to the second plus the square root of 2 times x to the third, and then plus 1. And again, I'm going to answer these three questions. So first of all, is it a polynomial? Well, the square root of 2 is not a power of x, so that's not an issue. We have an x to the second, an x to the third, and no x at all. So yes, this is in fact a polynomial. The leading coefficient is going to be the number in front of the highest power of x, and the number in front of the highest power of x is square root of 2. And that's a number, and so that is its leading coefficient. And the constant is going to be that number that isn't being multiplied by x at all, or if you like, is times x to the 0, and that's going to be 1. So the third example I'm going to do is maybe a little more complicated. I'm going to say y is equal to 2 times x plus 5 times x minus 1 to the second. Now, this is given in factored form. We can more easily identify what's going on here if we multiplied it all out, but I don't think any of us really wants to do that, and if we're clever, we don't have to. So if we were to multiply this all out, I hope you can see that you would get from this expression right here, you would get an x squared and then something with x and another constant. That x squared term, the highest power, is going to multiply this one, and that x to the second is going to become an x to the third, and then you would multiply by a constant, which is still going to leave the highest power of x as x to the third. All the rest of the stuff we multiply out is not going to create x to a negative exponent or to a fractional exponent, and so the answer to the first question, is this a polynomial? Yes, it is. And we've talked about also the answer to the, I meant to ask the degree question, so let me add that in. What is the degree of that polynomial? So I'll come that as our part D, I guess. So our leading coefficient, if we imagine multiplying that out, we would get a 1x squared here, and we would get times 1x would make a 1x to the third, times the 2 would give us a 2x to the third, which is going to make the leading coefficient be a positive 2. For the constant, if we multiplied this all out, the third term we would get here would be a plus 1. When we distributed everything there, eventually the 5 would multiply that 1 and become a 5, which in turn would get multiplied by that 2, which would make the constant be a 10. And the degree of this polynomial is going to be 3, because that's the highest power of x that appears. And on this one, the degree of the polynomial is going to be the highest power of x, which is 3. And on the first one, it doesn't really make sense to talk about degree because it's not a polynomial, but we could say, I guess, the highest power is going to be 5, but it really doesn't apply. I'm going to say NA for not applicable there. Okay, so save these 4 questions. I'm going to make a new page here and we'll continue. I've got a couple more examples here, and they're going to be a little bit more challenging, I believe. So here is going to be our next polynomial. We're going to say y is equal to a 4x minus 3 times x plus 1 times 3x plus 2, and then plus 2x to the fourth. So our first question, if we recall, is it a polynomial? And, well, if we multiply all that stuff out in factored form and add the 2x to the fourth, we are not going to get any fractional exponents or negative exponents, and so the answer is yes, it is indeed a polynomial. Secondly, we want to know what is the leading coefficient. Well, now we got to do a little bit of hunting. If we were to multiply this 4x times that x, we would get a 4x squared, times this 3x would give us a 12x to the third. But we're going to add it to that 2x to the fourth. They're not like terms, so they wouldn't combine. So 2x to the fourth is going to be that term that has the highest power of x, and its coefficient is 2. So the leading coefficient is 2. If we multiplied these all out, we would get a negative 3 would at some point in time multiply that 1 and become negative 3, which in turn would eventually multiply that 2 and be a negative 6. And the 2x to the fourth isn't going to influence that at all, so our constant is going to be a negative 6. And finally, the degree, like we said, when we multiply these three terms out, we're going to get a 12x to the third, but the 2x to the fourth is a higher power than that, so that makes it a fourth degree polynomial. Let's try another one. Let's do here, this is going to be a little more abstract. So we'll say y is equal to 3x to the n plus 2 plus 2x to the n minus 1 and plus 3x to the second. And I'm going to say that n is a positive integer. So because it is not a fraction or a negative number, then we can see here that all these powers are indeed positive integers. So yes, it is in fact going to be a polynomial. Now, if it's a positive integer, that means the smallest it can be is 1. So, but at any rate, the largest of these exponents between 2, n minus 1, and n plus 2 is going to be n plus 2. And maybe I should back up a moment to talk about part A. Because n is a positive integer, the smallest it could be is 1, and that would still make n minus 1 be 0. So we aren't going to get a negative exponent from there. So our answer to part A was still correct. It is indeed a polynomial. And the third question we're going to answer is, what is the leading coefficient? So the highest power of x is going to have to be the n plus 2. Since n is a positive integer, the smallest it could be is 1, plus 2 is 3. So that is going to be bigger than the 2 from 3x squared. So the degree of this polynomial is going to be n plus 2. I'm sorry, that was the answer to D, was the degree. So let me put the n plus 2 here. And the question that I wanted to answer, and now I'm not getting it to erase. Let me see if I can try that. I don't know why that's not working better. There we go. So the answer, the third question that we were asking is, what is the constant? And so in this case, we don't really know what the constant is. If n was equal to 1, then that would make n minus 1 be 0, and it would be, the constant would then be 2. So possibly it could be 2, but if n was bigger than 1, and all we know is that it's a positive integer, then there would be no constant at all, or I guess I would say it could be 0. So either it's going to be 2 or 0. That's a challenging one. I'm going to talk next about end behavior. So what we mean by end behavior in a polynomial, or in any function really, is what happens when we go way out to the right or way out to the left. That is, when you draw the graph, what is it going to look like way out to the right, way out to the left? This is sometimes referred to as long run behavior. Now, in a polynomial, we are going to get a graph of a polynomial is very nice in that it, in general, always, graphs of polynomials have very nice qualities that not all functions share. That is, they are going to always be continuous. That is, you can draw the graph of a polynomial without lifting your pencil from the paper. There aren't going to be any asymptotes. That is, there won't be vertical or horizontal asymptotes. So that's kind of a nice property to have. And they're what we would call smooth, which means there aren't going to be any sharp corner points or kinks or anything like that. So when we look at something like, say, as an example, y equals 2x to the third minus 5x plus 4, we're interested in, for the end behavior, is what do the graphs look like to the far right and to the far left. Symbolically, we can talk about that far right behavior, what we mean by what happens way out there to the right. The way we write it symbolically is to say the limit as x goes to positive infinity, and I'm going to give this a name so I don't have to keep writing it over again. So I'm going to call it f of x. Now, as we put in, what this means is, as we put in very large numbers for x, think 100, 1,000, 1,000,000, and so on. And I left off the cube. That was supposed to be cubed right there. And then a minus 5x plus 4. If you put in a big number like, say, 1,000, and you cube it, it's going to get huge. Way bigger even than what you might get from that minus 5 times 1,000. So we say that the behavior of this graph as x goes to positive infinity is going to be determined by the highest power of x and its coefficient. And when you put in a large positive number into x to the third, it will get cubed and still be positive, times the positive 2 is going to still be positive. So we're going to say that it's going to go to positive infinity. In terms of a graph, what that means is I don't really know what's going to happen in the middle of this graph at this point in time, but we do know that this graph way out to the right is going to go up towards positive infinity. And sometimes symbolically we'll write that as just an arrow up. The left-hand behavior, so what we call the left-end behavior, we would write symbolically as the limit as x goes to negative infinity of our function. And in this case, again, the behavior is going to be determined by the highest power of x and its coefficient. And in this case, when x is a large negative, say negative 1,000,000, cubed is still negative, times the 2 is still negative, so it's going to be what we would say is negative infinity. We might write that symbolically as going down. So whatever else the graph does in the middle, at the far left of the graph, it's going to be going down towards negative infinity. And so sometimes I would do this by showing my two hands in the air. When I ask for the end behavior of this function f of x, we would do something like this, where it's going to negative infinity on the left and to positive infinity on the right. Let's try another example. So I'm going to go to a new screen, and this time we're going to look at, say, y equals negative x to the fourth plus 5x to the third and minus 7. And again, we're looking for end behavior. So our end behavior, and again, when we just look at the highest power of x to get that indication, that's sometimes referred to as the leading coefficient test. So that leading coefficient test says formally what we talked about earlier, that the end behavior of this graph, what's going to happen way out to the far right and the far left, is going to be determined by the highest power of x and its coefficient. So again, using our limit notation, we would say the limit as x goes to positive infinity, and let me call this one g of x would be, and again, as you put in a large positive, to the fourth power is still positive, and then times the negative is going to be negative infinity. The limit as x goes to negative infinity of g of x, when you put in a large negative, to the fourth power is still going to be a positive, times that negative coefficient is going to be negative again. So whatever else this curve may do, we don't really know yet. We'll talk about more about that in the future, but we know to the far right and the far left, oops, it should go to negative infinity. Let me erase that. I put those as going to positive infinity. It should be going to negative infinity down, or we might just show that our end behavior is going to look like that. They're both going in the same direction. Okay, I want to talk about also what are called zeros of polynomials. In fact, I think I'm going to start a new page for this because I'm going to need a little bit more space. So let's talk about zeros of polynomials. So I'm going to write several different expressions or statements that are all equivalent. They all mean basically the same thing. So a zero of a polynomial is a value of x that makes our polynomial, or in fact any other kind of function, even if it's not a polynomial, that makes p of x equal to 0. So the reason it's called a zero is because it makes that equal to 0. Now these are also referred to as, so I'm going to say also known as X-intercepts, or at least they're related to that. They are similar. So an X-intercept is actually going to be an ordered pair, but a value of x that makes the polynomial 0 means that number comma 0 is going to be the X-intercept. Now that, if we're going to be very careful, is if x is a real number. So we will at various times be interested, we will restrict our domain to only real numbers, but other times we're going to allow imaginaries. So if something like, say, I made the polynomial equal to 0, it would still be considered a 0, but it's not going to be an X-intercept because our graphs are only going to be on the real plane. That is, x and y numbers can only be real when we graph. But other than that, an X-intercept and a 0 are going to be equivalent. They're going to be interchangeable. We'll also know these as roots of that polynomial. So if a value of x makes a polynomial equal to 0, that value of x is also a root, and we'll also refer to it as a solution. So sometimes you'll see it referred to as a solution to that equation p of x equals 0. So these four expressions are all equivalent. If a number makes the polynomial equal to 0, then that number comma 0 is, that ordered pair is an X-intercept, and it's also known as a root of the polynomial or a solution to p of x equals 0. Okay, let me ask you a different kind of question and see if you can figure this out. It's kind of challenging, I think. So given the polynomial p of x is equal to 3x to the 6th minus 2x to the 5th plus 4x to the 2nd minus 1. And we can see here from that polynomial, if you look carefully, so I'll say given, but you can see it, p of 0 is going to equal negative 1. So that means you can see when you plug in 0 for x, what you're going to get for y is a negative 1. So my question then is there reason to believe that P of X has and I could use any of those expressions that I wrote right above there, has a real X-intercept. Or I could have said, is there a real solution to P of X equals 0? Or is there a root to P of X? Or is there a real number that makes P of X equal to 0? So the thinking that can, and a justification perhaps, that can go to this is if we think about our n behavior, we can see that as x gets very, very large, then its n behavior is going to be determined by the highest power of x and its coefficient. And because that's an even power, whether you plug in a large negative or a large positive in there, to the 6th power will be positive, times 3 is going to be positive, so it's going to do something like that. Because we saw in the first part that we know this graph is going to go through 0, -1, since P of 0 is -1, and because this n behavior is going up, that means whatever else the function may do, somewhere it's got to end up going up there to the right, and so there must in fact be at least 2 places where, maybe more, but at least 2 places where this polynomial will cross the x-axis. And so the answer to that is yes, there must be an x-intercept, a real number x-intercept, because again, what we graph are real numbers, and in fact, there must be at least 2 of them. Okay, I hope this helps.